All right, so we have to do this last application of. Oh, hold, sorry. Are we going to be doing sequences in infinite series today? Possibly. Video on YouTube too, just if you can't get your internet to work. Yes, the video will be put up on YouTube. I'm also going to send you my notes that are hand worked, put them on Blackboard, so if you want to see those, you can as well. So we need to finish up Newton's law of cooling, and then we'll be done with the differential equations. That will technically finish everything we need for the next exam, which we will be taking soon. I believe what I've decided to do is I'm going to hold on just one second. What is the YouTube channel that this will be on? It is under, I think it's just Paul Berkins. I have to check and I'll send that to you. So the test, I haven't exactly decided. There's two options. One of them is to administer it through an online software service. Don't really care for that idea too much. So what I'm thinking of doing is posting the exam on Blackboard at class time, and then telling you that you have the class time to finish it and send it back to me. So you can just take pictures with your phone, you could scan it, however you can get that back. And then you would just email that to me. How do you guys feel about that format? All right, so it seems like everybody so far seems like they're okay with it. So you can change it up if it doesn't work the first time. Sounds good to me. Glad if you can be flexible. All right. So what I'm thinking is let's go ahead and finish Newton's law of cooling. We can start sequences and series. That will not be on the test, sequences and series. Next time on Thursday, we will review, and that'll make the test next Tuesday. So you'll have the weekend to prepare if you like. So please feel free to sound off on the chat if you have a complaint about that. But I want to go ahead and start this, guys, so we don't drag on too long here. I'm going to do my best not to keep you over time. So Newton's law of cooling, it's this formula right here. It's the derivative of temperature with respect to time. This K right here is a constant, and it's just a constant of proportionality. That's temperature, and T sub m is the temperature around the object. So if it's in a room, it has a particular temperature due to that area, and that's it. It's called T sub m. So I'm going to go ahead and solve the equation. Morning, Jimmy. And if you like, I'll do it both ways. It'll give you a little bit of review of differential equations. So they give us this example here. I'm just going to go ahead and push that off to the side for a second just to solve the equation first. So let me make sure I got the marker that works well. Can't really see that one too well. Just bought a whole box of markers and none of them want to seem to work. No, it's not bad. Okay. So we have the derivative of temperature with respect to time is equal to a constant times temperature minus Tm. So K and Tm are just constants. We can solve this two different ways. Let's see, I'm going to first multiply this K through over here. So this is KT minus KTM. Now, if I take the KT term to the left-hand side, I have the derivative of temperature with respect to time minus KT equals negative KTM. So that is in the form of integrating factor. All right, so remember that that is dy dx plus p of x y equals some q of x. Or in our case, dt, right? D big T, D little t is the best way I can say it, or D temperature with respect to time. Here instead of y we have t, and then over here we just have a constant, so that's okay. So here in our case, this would be p of t. So our integrating factor mu is e to the integral of minus k. Right, because it's supposed to be plus, so if you want you could always make this plus a negative. So this is minus k dt. That's a very simple integral, so that is e to the minus kt. Remember that we take our integrating factor and we multiply it through the entire equation. So we come over here. This is e to the minus kt, derivative of temperature with respect to time, minus k, and I'm going to write the e here. Alright, so now we've got that this side should collapse, as always, to the derivative, in this case with respect to t, of the integrating factor, e to the minus kt, times the variable the integral is over, which is t. And on this side we just leave it alone. So then we need to make sure that this side is what we claim it is. So if we take the derivative of big T here and leave the e alone, we get this term. And if we take the derivative of e to the minus kt, we would get a minus k in front. So we'd have minus k e to the minus kt, and we leave temperature alone. So this is correct. We just need to then take this dt, slide it to the other side. So we have d e to the minus kt times temperature, and then over here we just need a dt. We can integrate at this point. So integrate both sides. This side's always lovely because this is going to fall right out. So this is going to be e to the minus kt times temperature. The right-hand side, we could do a u substitution. So we have e to the minus kt there. So if I let u equal minus kt, the derivative gives me back minus k, which means this is really e to the u du. Or, basically when I integrate, I just get back Tm times E. And of course, we have to add in some constant there. Excuse me. Everybody okay so far? And I apologize for the pause, but there is a delay in the chat, so I'm not sure if you guys are typing your questions or if you're all just perfectly fine right where you are. Can you do the last thing again? So you're talking about the integral right here, I'm guessing. So let u equal minus kt. Du is then minus k dt. Minus k dt right there. Tm is a constant. You could throw that out in front. This becomes integral, well, we throw the Tm out front, e to the u du, right? We all know that that just gives us back e to the u, which is e to the minus kt, and the Tm stays. So we're at this point, the last thing we want is t equals, so we would divide every single term by e to the minus kt. So we would be left with t equals Tm plus c e to the positive kt. Alright, so Brentley, the step above, is that what happened to the k on the left side? Are you talking about this k? Or somewhere else? Okay, so this k right here, we redid this is the product rule in reverse, and this k right here comes from taking the derivative of this guy. Or if I take the derivative of e to the minus kt, I get a minus k e to the minus kt. Like, make that a 2, right? E to the 2t is 2e to the 2t. So that's where this minus k comes from, and because we're writing it in reverse, it gets absorbed back into the term. Okay. So this is our end result. And so any problem I give you, what I'm actually going to ask you to do is solve the equation from here. You can do this without any numbers plugged in if you choose. The only number that's going to be given that you can plug in is Tm. But I don't want you to just start here, because that doesn't prove to me that you can solve differential equations. That just proves that you understand, or you take my result as truth and then plug numbers in. So we're going to use this equation. I'm actually going to solve this one more time, like I said, as a good review for you. So any objection to me erasing the board? No objection, nice. You also, if you need to, can take a screenshot if you really want. And like I said, I'm going to put the recordings up on YouTube, and I'll get that page to you today. And of course, I'm going to give you my notes when I get a chance to get that out to you. It just does not want to erase today. Let me try the other eraser. See if it works better. The notes without the work are on Blackboard already. I am going to put the notes with my work on there at some point so that you guys can look at those. Not much better. That looks terrible. I gotta put up with this for a month? My goodness. Did you have to buy your own erase board for this? Absolutely I did. I went to Office Depot on Sunday and picked this bad boy up. Just wipe this down real quick. Ooh. So I left the result here because I want to do it the other way and prove that I get the same thing. So we just did integrating factors, so what is the other method that I could use? What's the only other method we learned? There's also separation of variables. So let's do it that way. So this term right here has temperature and a constant. So I can put it with the dt here, and I can move this dt to the other side. That's now properly separated. I can integrate both sides. When I integrate this side, I'm going to get natural log of t minus tm. And when I integrate this side, I'm going to get kt plus some constant. So I want to get t by itself. I can get rid of that log by taking e of both sides. These then cancel. I have t minus tm is equal to, this is e to the kt plus c. However, remember that if I have two exponents up here added together, I can break these into a multiplication. So this is e to the kt times e to the c. And e is just some number, and so some number to a constant is just yet another constant. So I'm going to call that C1. So that's all going to result in t minus tm equal to C1 e to the kt. And if I move the tm over, I once again get t equals tm plus C1 e to the kt. So doing it either way, you can get the correct result. I don't care which one you choose, just do the one that you feel most comfortable with. Personally think that one's easier, but it's probably not as easy to recognize that you can do it that way. You may not use either method for any problem. For any Newton's method you can, but for any differential equation that's not the case. There are very specific ways that certain problems must be solved. The real key is anytime that you have the variable minus a constant term, this type of setup is always something you could do both ways. And k could be 1, right? So that type of problem can be done both ways. All right, so if we are okay with the result, I'd like to use it to solve this problem now, so we can go ahead and move on to some sequences and series. All right, so let's look at this actual problem here. So it says a cake is removed from an oven and placed into a room with temperature 70 degrees. That right there is your T sub m. That is the temperature of the surroundings, right, around the object. Its temperature is initially known to be 300 Fahrenheit. So that means the temperature at time t equals 0 is 300. After 3 minutes, the cake's temperature is 200 degrees. So that means T of 3 is 200. Can you guys see those okay over there? Okay. So, find a function for the temperature that gives the temperature at any time t, and once you have that, how long would it take until the cake is safely at a safe temperature to be eaten? So again, let me move this off the screen so we can maximize the surface. Alright, so I'm going to start with this equation. I have that the temperature, because I've already solved it, the temperature is equal to 70 plus C1 e to the kt. So my job now is to find C1 and K. I need to use my initial conditions. So you might think, oh, I can use either of them. But in fact, you must use the first one. And the reason is that when I plug in time, little t is 0, then this guy goes to 1. Alright, I'll give you guys a second. Seems like a lot of you are having some trouble there. Okay, I'll wait. Okay, so I'm going to go ahead and stop and then restart. I don't know what the F means, everybody.